The late Cretaceous period. We often imagine it as a lost world of savage titans, a relentless clash of giants. But reality was infinitely more complex and far more crowded. This was a planet teeming with life on a scale that defies the modern imagination. From the humid, towering forests of North America to the vast floodplains of South America, every conceivable environment was occupied. The air, thick with moisture and the scent of primordial flora, hummed with the beat of pterosaur wings. The ground itself seemed to breathe, trembling under the weight of sauropod herds that moved like living mountain ranges. And in the dense undergrowth, a million smaller dramas played out, unseen and unheard by their colossal neighbors. This wasn't just a random collection of species. It was a deeply interconnected, interwoven tapestry of life, a biological puzzle of coexistence on an epic scale. The fundamental question isn't simply how these incredible animals lived, but how they all lived together. How did a single ecosystem support such a staggering concentration of colossal herbivores and the formidable predators that relentlessly pursued them? The answer lies not in constant conflict, but in a delicate, evolutionary ballet of specialization that allowed for a precarious peace. The foundation of this crowded world was a crucial ecological concept, niche partitioning. To understand it, imagine a planetary supermarket where every shelf, from the muddy floor to the highest canopy, is stocked with a different kind of food. The herbivores of the Mesozoic were nature's master shoppers, each exquisitely adapted to browse on a specific shelf. Towering above all were the last of the great sauropods, like the colossal Alamosaurus. With their impossibly long necks, they were the exclusive high browsers, harvesting foliage from the tops of ancient conifers and cycads, a food source far beyond the reach of any other contemporary plant eater. They occupied a feeding zone entirely their own, converting sunlight energy captured by the highest leaves into flesh and bone. Down below, on the forest floor, a completely different strategy was at play. Ankylosaurus, the armored tank of the Cretaceous, was a low-level specialist. Its short, powerful stature and broad beak were perfectly designed for cropping vast quantities of ferns, low-growing shrubs, and other ground cover. It wasn't competing with Alamosaurus for a single leaf, any more than a whale competes with an eagle. They shared the same domain, but operated in entirely different vertical worlds. This vertical division of resources was just the first layer of complexity. Among the numerous ground-level feeders, further specialization was absolutely essential for survival. Let's consider two of the most successful and abundant groups of the late Cretaceous, the hadrosaurs and the ceratopsians. The famous duck-billed hadrosaurs, such as Edmontosaurus, possessed some of the most sophisticated dental hardware ever to evolve. Hundreds upon hundreds of teeth were packed tightly together, forming vast grinding surfaces capable of pulverizing the toughest, lowest quality vegetation, including twigs, bark, and coarse needles. They were the unstoppable bulk browsers, consuming enormous quantities of plant matter with little discrimination. In stark contrast, the ceratopsians, like the iconic Triceratops, brought a different toolkit to the table. Their sharp, powerful, parrot-like beaks were perfect for snipping specific, tough plants, particularly fibrous cycads and palms that other herbivores might ignore. Their shearing batteries of teeth then sliced this challenging material with incredible efficiency. In essence, one was a lawnmower, the other a set of industrial pruning shears. By specializing in different types of flora at the exact same height, they could thrive side by side in vast mingling herds, minimizing direct competition and maximizing the use of the available resources. This intricate partitioning of the world wasn't a phenomenon exclusive to the plant eaters. A landscape filled with such an abundance and variety of prey inevitably supported a diverse and stratified guild of predators, each with its own preferred hunting strategy, technique, and target. At the absolute pinnacle stood the apex predator, Tyrannosaurus rex, a specialist in confronting the largest and most dangerous herbivores of its time. Its incredible size, reinforced skeleton, and legendary bone-crushing bite were all adaptations for tackling formidable, multi-ton prey like Triceratops and Edmontosaurus. A mature T-Rex would have largely ignored smaller, faster animals, as the energetic cost of a chase would not justify the meager reward. That vital ecological space was filled by others. Operating in the shadows of these giants were packs of smaller, more agile theropods, like the formidable dromaeosaur Dakota raptor. Gifted with speed, sharp senses, and their trademark sickle claws, they were perfectly equipped to hunt the smaller ornithopods, unwary juvenile dinosaurs, or other fleet-footed prey that the colossal Tyrannosaurus couldn't efficiently pursue. Each predator, large and small, played a specific, crucial role, ensuring that predatory pressure was applied across the entire ecosystem, preventing any single herbivore group from dominating the landscape. Beyond what they ate, coexistence was also masterfully managed by when and where these animals lived their lives. Ecologists refer to this as temporal and spatial partitioning. While direct fossil evidence for time-of-day activity is scarce, modern ecosystems provide a compelling model. It is highly plausible that some smaller predators and herbivores were primarily nocturnal, emerging to hunt and forage under the cool cover of darkness, while the larger, diurnal dinosaurs rested. This would have opened up a whole new world of opportunity, dramatically reducing direct conflict for resources and space. Furthermore, even within the same vast geographic region, dinosaurs showed clear preferences for specific microhabitats. Fossil evidence from formations like Hell Creek in North America reveals a rich mosaic of environments: dense redwood forests, open fern-covered floodplains, murky swamps, and winding riverbanks. The lumbering, heavily armored Ankylosaurus may have preferred the protective cover of dense forests, while vast, vulnerable herds of Edmontosaurus congregated on the open plains, where they could spot danger from afar. This geographical separation meant that even species with similar diets could thrive in the same territory without constantly competing for every leaf and every watering hole. Perhaps the most fascinating and efficient aspect of this crowded world was that dinosaurs didn't just partition niches between different species, but also within their own incredibly long life cycles. A hatchling Tyrannosaurus rex, no larger than a modern turkey, was a fragile creature. It certainly wasn't equipped to hunt a 10-ton Triceratops. For the first several years of their lives, young Tyrannosaurus were likely fast, slender, long-legged predators, filling the ecological niche of a medium-sized carnivore. Their diet would have consisted of lizards, early mammals, and the juveniles of other dinosaurs. As they aged, their bodies underwent a radical transformation. Their legs became more robust and pillar-like, built for supporting immense weight rather than for pure speed. And their skulls deepened and widened to house those devastating, bone-shattering muscles. Their ecological role and their preferred prey shifted in lockstep with their physical changes. This ontogenetic niche shifting meant that a single species like Tyrannosaurus rex could function as several distinct predators throughout its life. It wasn't just one animal, it was an ecological dynasty, starting as a nimble hunter of small game and maturing into the undisputed monarch of its domain. This incredible strategy vastly increased the carrying capacity of the environment. The world of the dinosaurs, viewed through this lens, was therefore not a chaotic, perpetual battle for survival, but a breathtaking testament to millions of years of evolutionary precision. It was a finely tuned, self-regulating system, a complex web of interactions, where every creature, from the smallest insect eaters scurrying in the undergrowth to the largest sauropod browsing the canopy, had a specific and vital role. Niche partitioning, achieved by diet, by size, by habitat, by time of day, and even by age, was the invisible architecture that allowed this planet of giants to function and flourish. It allowed for a level of biodiversity and a total biomass that the modern world can scarcely comprehend. The Earth was truly saturated with life. When the asteroid struck 66 million years ago, it did more than just extinguish individual species. It shattered this intricate, delicate structure, collapsing the carefully constructed ecological pyramid that had been built over eons. Understanding how they all fit together gives us a profound new appreciation not for the dinosaurs themselves, but for the fragile balance that governs all life on Earth, then and now. It is a powerful reminder that every ecosystem is far more than the sum of its parts. It is a shared domain, a carefully negotiated peace on a very, very crowded planet. Our planet's story is one of profound transformation, written in layers of rock. 252 million years ago, this story almost ended. The Great Dying, the Permian-Triassic extinction event, scoured the globe, extinguishing over 90% of marine species and 70% of terrestrial life. From this near-total silence, a new world struggled to be born. This is the Triassic period, the dawn of a new age on a single colossal landmass, Pangaea. The climate was harsh and unforgiving, a world of extremes. Vast arid deserts baked under a relentless sun, while immense monsoon systems brought seasonal deluges to the coastal regions. Life clung to the margins, in river valleys and along the coasts. Hardy plants like conifers, cycads, and ferns formed the backbone of these recovering ecosystems. In this crucible of creation, life began to experiment, giving rise to new forms and new dynasties. Among them, a group of reptiles was poised to inherit the Earth. But their path to dominance was far from guaranteed. They were not yet giants, but pioneers in a strange and hostile land. Before the dinosaurs, there were other rulers. The survivors of the Great Dying radiated into the vacant ecological roles, and a group known as the archosaurs, or ruling reptiles, rose to prominence. They split into two great lineages. One, the Cretaceans, represented the ancestors of modern crocodilians, and in the Triassic, they were the undisputed apex predators. Creatures like Postosuchus were the lions of their time. Nearly 20 feet long, this formidable hunter walked on 4 pillar-like legs, a departure from the sprawling gait of its more distant relatives. Its skull was deep and powerful, lined with blade-like teeth, perfectly suited for tackling the tough-hided herbivores of the period. Postosuchus and its kin were terrestrial terrors, embodying a successful and powerful body plan. They patrolled the Triassic floodplains with an air of authority, their heavy footfalls a constant reminder of who truly controlled this recovering world. For any smaller creature, the shadow of a Cretacean was the very definition of danger. They were the established power, the old guard of the Archosaur Empire. Meanwhile, the other great Archosaur branch, the Avemetatarsallians, the line leading to birds and dinosaurs, was forging a different path. Their evolutionary innovation was revolutionary, a fully upright posture. With their legs positioned directly beneath their bodies, they could move with greater speed and efficiency than their sprawling cousins. From this lineage, the first true dinosaurs emerged. They were not titans. Creatures like Eoraptor, the dawn plunderer, were small, barely 3 feet long. They were bipedal, freeing their hands for grasping and manipulating objects. This combination of an efficient stance, bipedal locomotion, and dexterous forelimbs was their secret weapon. It allowed them to be swift, agile, and adaptable. While the massive Cretaceous dominated through sheer power, these early dinosaurs thrived on the periphery. They were opportunistic hunters and scavengers, living in the shadows of the giants. They were a blueprint for a new kind of animal, a design built for endurance and adaptability. Their time had not yet come, but the foundations for a future dynasty, one that would last for over 150 million years, were being laid. The Triassic world was not a simple, two-sided conflict between dinosaurs and their Cretaceous relatives. It was a complex and crowded stage filled with a bizarre and fascinating cast of characters. Among the most successful herbivores were the Dicynodonts, holdovers from the Permian period. Tusked, barrel-chested, and pig-like in their habits, creatures such as Placerius browsed in large herds, using their powerful beaks and tusks to dig for roots and tubers. They shared the landscape with rhynchosaurs, stout reptiles with incredibly strange, shearing beaks, perfectly adapted for slicing through tough plant material. And scurrying through the undergrowth, often unnoticed, were the cynodonts. Small, furry, and warm-blooded, these creatures were not reptiles, but synapsids, members of the lineage that would eventually give rise to all mammals, including ourselves. They were a glimpse of a distant future, surviving and adapting in a world governed by reptilian giants. This intricate web of life, a mosaic of old dynasties and new experiments, highlights a crucial truth. The first dinosaurs were not colonizing an empty world, but carving out a niche in a vibrant, established, and highly competitive ecosystem. As the Triassic progressed, the dinosaurs began to diversify, and one group made a monumental evolutionary leap. These were the sauropodomorphs, the ancestors of the colossal long-necked sauropods of the Jurassic. Early forms like Brachiosaurus from the late Triassic were the first dinosaurs to achieve truly large size. Reaching up to 30 feet in length, they were facultative bipeds, capable of walking on all fours, but also rearing up on their powerful hind legs to reach high into the canopies of conifer trees. This ability opened up a food source previously unavailable to terrestrial herbivores. Their long necks, small heads, and peg-like teeth were designed for stripping foliage, which was then ground down in their massive digestive tracts. Fossil discoveries of multiple Plateosaurus skeletons together in bone beds suggest they may have moved in social groups or herds, perhaps migrating to follow seasonal rains and fresh vegetation. They were a testament to the success of the dinosaur body plan, a walking, breathing testament to how this once modest group was beginning to redefine the rules of life on land. While life on the ground was becoming a complex theater of competition and innovation, another evolutionary frontier was being conquered. In the skies above the Triassic landscape, a new kind of reptile took flight. These were the pterosaurs, close cousins of the dinosaurs, but not dinosaurs themselves. They were the first vertebrates ever to achieve powered flight. Early species like Eudimorphodon were relatively small, with wingspans of about 3 feet. Their wings were not made of feathers, but of a tough, leathery membrane of skin and muscle, stretched between their body and a dramatically elongated fourth finger. This unique anatomical structure allowed for incredible agility in the air. With lightweight, hollow bones and keen eyesight, Eudimorphodon was likely an expert aerial hunter. Its long jaws lined with sharp, needle-like teeth, perfectly suited for snatching insects out of the air or skimming fish from the surface of lakes and coastal waters. Their ascent represented another successful offshoot of the Archosaur family tree, a masterful adaptation that claimed the air as a new domain. For 30 million years, this diverse Triassic world thrived, a dynamic balance of strange and wonderful creatures. But the planet's story is one of cyclical catastrophe and renewal. Around 201 million years ago, as the Triassic period drew to a close, the supercontinent Pangaea began to break apart. This rifting unleashed one of the largest volcanic events in Earth's history. For hundreds of thousands of years, the Central Atlantic magmatic province spewed lava and greenhouse gases, triggering catastrophic climate change and ocean acidification. This was the Triassic-Jurassic extinction event. The great Crurotarsans, the dominant Dicynodonts, and many other established groups could not adapt. They vanished. Yet, remarkably, many dinosaur lineages survived. Perhaps their more efficient breathing, their adaptable metabolism, or simply being in the right place at the right time allowed them to weather the storm. The slate had been wiped clean. The niches once held by their powerful competitors were now empty. The humble pioneers of the early Triassic had been given their opportunity. The blueprint was complete. A new era was dawning, an era that would belong unequivocally to the dinosaurs. The Jurassic period, a world painted in shades of green, under a warmer, more humid sky. This was an age of titans, a time when the biomass of terrestrial life reached a scale difficult to comprehend. Vast forests of conifers, cycads, and ginkgos stood silent witness to the reign of the dinosaurs. And among them, the herbivores were the true architects of the landscape. Colossal sauropods, armored stegosaurs, and nimble ornithopods populated every corner of the supercontinent Pangaea. But this abundance presents a profound ecological puzzle. How could so many enormous animals, all plant eaters, coexist in the same environment without stripping it bare? How did they avoid constant, desperate competition for the same food sources? The answer is not one of conflict, but of elegant separation. It lies in a strategy that life has used time and again, a vertical division of resources that transformed the Jurassic forest into a structured, multi-level banquet hall, ensuring there was enough for everyone. This is the story of a vertical divide, a peaceful solution to sharing a planet. At the very top of this living architecture were the high browsers, sauropods of the brachiosaurid family. Giants like Brachiosaurus and Giraffitan were masters of the canopy. Their anatomy was a marvel of biological engineering, perfectly suited for reaching heights no other contemporary animal could dream of. Unlike their sauropod cousins, their front limbs were longer than their hind limbs, creating a steeply inclined back that naturally elevated their neck space. This posture, combined with a neck that could measure over 30 feet, allowed them to graze on the tender leaves and cones of the tallest trees, 40 or even 50 feet above the ground. They were the giraffes of their time, but on an altogether more massive scale. Occupying this exclusive sun-drenched niche, they harvested solar energy captured by the highest leaves, effectively avoiding any dietary overlap with the myriad of herbivores foraging far below. Their specialized feeding strategy was the first and highest tier in the Jurassic's vertical ecosystem, a testament to evolution's ability to find opportunity in every available space. Descending from the canopy, we find the next tier occupied by a different family of sauropods, the Diplodocusids. Dinosaurs like Diplodocus and Apatosaurus were just as immense as the Brachiosaurs, but they were built for a completely different feeding strategy. Their bodies were structured like massive suspension bridges, with front legs shorter than their hind legs, resulting in a horizontal posture. Their necks, while incredibly long, were held more parallel to the ground. This adaptation didn't allow them to reach the treetops, but it gave them an incredible feeding radius. Like a colossal living crane, a Diplodocus could stand in one spot and sweep its head and neck over a vast area of mid-level vegetation. They were bulk feeders, consuming enormous quantities of ferns, cycads, and horsetails that grew in sprawling, open woodlands or fern prairies. Their peg-like teeth were perfect for stripping foliage from branches, leaving the finer chewing to their gizzards. This horizontal approach carved out a distinct feeding zone, a middle-story world untouched by the high-browsing brachiosaurs above. Further down the vertical ladder, we encounter one of the most recognizable herbivores of the Jurassic, the Stegosaurus. While still a large animal, its world was defined by what grew closer to the forest floor. Its head was small and carried low to the ground, a position dictated by its short forelimbs. This posture made it a specialist in low browsing. Unlike the sauropods that stripped entire branches, Stegosaurus had a narrow beak, or rhamphotheca, which it used to selectively snip off the fronds of ferns, the leaves of young cycads, and other soft, ground-level vegetation. Its teeth were small and simple, suggesting it didn't do much chewing, relying instead on gastroliths in its stomach to grind its food. This focus on the lower stratum of the plant world placed it in a feeding niche entirely separate from the towering sauropods. While its famous back plates likely served for display or thermoregulation, and its tail spikes, the thagomizer, were a formidable defense, its primary daily existence was a quiet one, spent methodically harvesting the bounty of the understory. At the very base of the ecosystem, on the forest floor itself, lived the smallest and most agile of the Jurassic herbivores. Ornithopods like Dryosaurus and Camptosaurus were dynamic and nimble browsers. Too small to compete with the bulk-feeding stegosaurs and certainly unable to reach the heights of the sauropods, they carved out a niche as selective ground-level feeders. Moving in small herds, they would have darted through the legs of their larger neighbors, their keen senses ever alert for predators. With more sophisticated jaws and cheeks than the stegosaurs, they could chew their food more effectively, allowing them to process tougher plant material found at the very bottom of the food chain. Low-growing shrubs, ground cover, and perhaps even fallen seeds and fruits from the trees above. They were the opportunists, the careful foragers, who cleaned up the lowest level of the Jurassic banquet hall. Their existence demonstrates the incredible granularity of this niche partitioning, where even the forest floor was subdivided to support different forms of life and feeding strategies. When we step back and view this entire system, the Jurassic forest reveals itself not as a random collection of creatures, but as a highly organized, living metropolis. It was a cathedral of foliage, with each level, each vault and alcove supporting a different resident. High in the canopy, the brachiosaurs grazed in the sun, their long necks like living elevators to an exclusive buffet. Below them, the Diplodocusids swept through the mid-level clearings, their horizontal necks harvesting vegetation across vast swaths of land. Beneath them, the stegosaurs methodically worked their way through the dense understory, their armored bodies perfectly adapted for a life among the ferns. And on the ground floor, the small, swift ornithopods picked and chose from the remaining bounty, darting between the feet of the giants. There was no direct competition for food between a Brachiosaurus and a Dryosaurus. They lived in the same forest, but inhabited entirely different worlds, separated by height. This vertical partitioning created a stable, incredibly productive ecosystem, allowing for a density and diversity of megafauna that has rarely been matched in Earth's history. This elegant solution of niche partitioning is not merely a relic of the Jurassic. It is a fundamental principle of ecology, a timeless strategy for coexistence that we see echoed in ecosystems today. In the African savanna, giraffes browse the high branches, while zebra graze on grasses, and dik-diks nibble on low shrubs. The Jurassic giants, in their own magnificent way, were pioneers of this strategy on a truly titanic scale. Their vertical divide was a key factor in their success, allowing them to dominate the planet for tens of millions of years. It reminds us that these were not clumsy monsters stumbling through a primitive world. They were sophisticated animals, integral parts of a complex and finely balanced environmental machine. The legacy of the Jurassic is not just one of size, but of intricacy. It is a lesson written in the fossil record, telling of a world where giants learned to share their domain, not through conflict, but by simply looking up, looking down, and finding their own place in the sun. The late Jurassic period, 150 million years ago. This is the Morrison Formation of North America, a vast semi-arid floodplain stretching across what will one day become the western United States. It is a world of giants, dominated by the colossal forms of sauropods like Diplodocus and Brachiosaurus, their herds shaping the very landscape they traverse. Armored Stegosaurus and nimble Camptosaurus browse through ancient cycads and ferns. But where there is prey, there must be predators, and the Morrison was home to a truly fearsome array of carnivores. This presents a paleontological puzzle. In a stable ecosystem, how can multiple large apex predators coexist without driving one another to extinction? The landscape was dominated by the formidable Allosaurus, the undisputed lion of the Jurassic. Yet it was not alone. Sharing this domain was the equally intimidating horn-nosed Ceratopsians. This was not a simple two-player game. Other large theropods, like the massive Torvosaurus, also prowled these lands. The survival of so many hunters in one place was not an accident of nature, but the result of an unspoken evolutionary agreement, a compact between carnivores that allowed this vibrant, dangerous world to flourish. Let us first consider the tyrant of this domain, Allosaurus. Reaching lengths of up to 12 meters, it was a perfectly engineered predator. Its massive skull was surprisingly light for its size, built with openings or fenestrae that reduced weight without compromising strength. This was not a skull designed for a crushing bite like that of the later Tyrannosaurus. Instead, paleontologists theorize a different, terrifyingly effective hunting method. Allosaurus likely used its powerful neck muscles to drive its upper jaw downwards, using its serrated teeth like the blade of a hatchet. This would inflict deep, catastrophic wounds on even the largest of sauropods, causing massive blood loss. Its arms, far from being useless, were strong and tipped with 3 enormous recurved claws, ideal for gripping struggling prey. Analysis of its brain case suggests a sophisticated sense of smell and good, if not exceptional, vision. Allosaurus was an ambush hunter, a creature of immense power built to tackle the giants of its age, carving out the role of the primary mega-predator on the open plains. But Allosaurus did not hunt unchallenged. Stalking the same ancient world was Ceratosaurus. Though not as large as its contemporary, it was a formidable predator in its own right, reaching up to 7 meters in length. Its name, meaning horned lizard, points to its most striking feature, a prominent, blade-like horn on its snout, with smaller hornlets over its eyes. The exact function of this ornamentation is debated. It may have been purely for display, to attract mates or intimidate rivals, a vibrant signal in a world of greens and browns. Anatomically, Ceratosaurus was distinct. It had a longer, more flexible, serpentine body and a deep, powerful tail. A row of bony plates, called osteoderms, ran along its spine, offering some measure of protection. Its teeth were proportionally longer and more blade-like than those of Allosaurus. These differences are not trivial. They are crucial clues, adaptations that suggest Ceratosaurus was not simply a smaller version of Allosaurus, but a different kind of hunter altogether, playing by a different set of rules. The key to this prehistoric coexistence is a fundamental ecological principle known as niche partitioning. In any given habitat, direct competition is evolutionarily expensive. It leads to injury, wasted energy, and potential extinction. Nature's solution is specialization. Different species evolve to utilize different resources, effectively dividing the environment into separate niches. It's the same principle we see today in the African savanna, where lions, leopards, and cheetahs hunt in the same territory but largely avoid conflict by targeting different prey, hunting at different times, or using different areas of the landscape. The Morrison Formation was a grander stage for this same evolutionary play. Allosaurus, with its robust build, was adapted for the high-risk, high-reward pursuit of giant sauropods and armored stegosaurs on the open floodplains. Ceratopsians, smaller and more agile, likely carved out a niche elsewhere, avoiding direct confrontation with its larger cousin. This carnivore's compact was not a conscious treaty, but a partitioning of the world driven by anatomy and instinct, ensuring survival through separation. This theory is not mere speculation, it is written in the fossil record. Paleontologists act as detectives, piecing together this ancient drama from clues left in stone. The most compelling evidence comes from bite marks. On the fossilized bones of Allosaurus's preferred prey, sauropods and Stegosaurus, we find deep gouges and punctures. When we match these marks to the teeth of known predators, the culprit is unmistakable. The size, shape, and spacing perfectly align with the dental arsenal of Allosaurus. In one famous example, an Allosaurus pubis bone shows a wound from the tail spike of a Stegosaurus, a clear record of a violent encounter. Conversely, such evidence linking ceratopsians to these giant herbivores is notably absent. The fossils tell a story of population as well. At sites like the Cleveland Lloyd Dinosaur Quarry in Utah, the remains of at least 44 Allosaurus individuals have been found, compared to just a single Ceratosaurus. This disparity suggests Allosaurus was far more common, or at least congregated more frequently, in these specific floodplain environments, reinforcing the idea that they occupied different, though occasionally overlapping domains. So, if Ceratosaurus wasn't regularly tackling giants, what was its specialty? Its anatomy offers compelling hints. The long, deep, and flexible tail is reminiscent of modern crocodilians, suggesting it was a capable swimmer. Its habitat may have been centered around the rivers, lakes, and wetlands that crisscrossed the Morrison landscape, areas the larger, more terrestrially built Allosaurus might have found cumbersome. In these aquatic adjacent zones, a different menu of prey was available. Ancient fish, turtles, and primitive crocodiles would have been plentiful. Furthermore, the riverbanks would have been a magnet for smaller, faster dinosaurs coming to drink, such as the ornithotod Dryosaurus. The longer, narrower teeth of Ceratopsians would have been better suited for gripping such smaller, struggling prey than for inflicting hatchet-like wounds on a sauropod. It was likely a wetland specialist, an opportunist that thrived at the water's edge, skillfully exploiting a resource-rich environment that its larger competitors were not as well equipped to dominate. It survived not by challenging the king, but ruling its own separate province. The world of the Morrison Formation, therefore, was not a chaotic, perpetual war between titans. It was a finely tuned ecosystem, a complex mosaic of overlapping territories and specialized roles. Its success was predicated on this intricate balance, this carnivore's compact. Allosaurus was the powerhouse of the plains, a hunter of giants. Torvosaurus, even larger and more robust, may have been a rarer apex predator, specializing in the largest of all prey, or perhaps a formidable scavenger. And Ceratopsians was the master of the margins, a swift and adaptable hunter thriving in the wetlands and riverine forests. Each predator, shaped by millions of years of evolution, was a unique key unlocking a different set of resources within the environment. This division of roles prevented destructive head-on competition, allowing for a diversity of large carnivores unparalleled in many of today's ecosystems. They shared a planet not through peace, but through purpose, each playing its vital part in the grand, savage, and magnificent theater of the dinosaur domains. The Cretaceous period was a world in transformation. The continents continued their slow drift, oceans rose, and the climate warmed. But the most profound revolution was happening at a smaller scale, in the soil. A new type of plant, the angiosperm, or flowering plant, had arrived. This botanical innovation triggered an evolutionary cascade, providing a vast and rapidly regenerating food source unlike anything the world had seen before. In response, herbivorous dinosaurs diversified at an explosive rate. Two groups in particular rose to unparalleled prominence, becoming the undisputed architects of these new landscapes. These were the hadrosaurs, the duck-billed dinosaurs with their incredible dental machinery, and the ceratopsians, the horned dinosaurs with their formidable defensive shields. For millions of years, these two great dynasties would share the plains, forests, and floodplains of the late Cretaceous, their immense herds carving out a shared existence in a world of plenty. This was their domain, the Cretaceous Commons, a global pasture supporting a biomass of herbivores that would dwarf anything on Earth today. The hadrosaurs were the quintessential success story of the late Cretaceous. Often called the cattle of the Cretaceous, their numbers were staggering, with fossil evidence suggesting they formed immense herds that roamed across entire continents. Their defining feature was their namesake, duckbill, a broad, toothless beak perfect for cropping vegetation. But their true evolutionary marvel lay deeper inside. Their mouths were packed with hundreds, sometimes thousands of teeth, fused into complex grinding surfaces called dental batteries. As teeth wore down, new ones constantly erupted from below, creating a perpetually sharp and efficient milling surface. This allowed them to process even the toughest plant material, from conifer needles to fibrous twigs. Furthermore, Many species, like the famous Parasaurolophus, possessed elaborate, hollow crests connected to their nasal passages. Far from being simple ornaments, these were likely sophisticated resonating chambers, allowing individuals to produce deep, powerful calls to communicate across vast distances, coordinating herd movements and warning of danger. While hadrosaurs dominated the browsing niches, another group laid claim to the lower strata of vegetation, the ceratopsians. Their evolutionary tale is one of remarkable scaling up. From small bipedal ancestors in the early Cretaceous, they evolved into the colossal, tank-like quadrupeds that defined the end of the Mesozoic era. The most famous of their kind, Triceratops, was a walking fortress. Its skull alone could be over 2 meters long, a solid structure of bone equipped with a powerful shearing beak for slicing through tough, low-growing plants like cycads and ferns, which other herbivores might ignore. Anchoring this powerful jaw was a massive frill of bone flaring from the back of the skull. While providing a robust anchor for jaw muscles and some protection for the neck, its primary function was likely display, a vibrant billboard advertising an individual's health and status. And, of course, the horns, brow horns that could exceed a meter in length and a smaller nasal horn, were not just for show. They were potent weapons used for intraspecific combat and as a formidable defense against the era's apex predators. The sight of vast herds of Edmontosaurus mingling with groups of Triceratops raises a critical ecological question. How did so many large herbivores coexist? The answer lies in a fundamental ecological principle known as niche partitioning. These two dominant groups, despite living side by side, were not in direct, constant competition for food. They effectively divided the resources of their shared environment. Hadrosaurs, with their greater height and flexible necks, were primarily browsers. They could reach higher into the foliage of conifers and early flowering trees, stripping leaves and twigs well above the ground. Ceratopsians, conversely, were specialized low-level grazers. Their powerful beaks and stocky, low-slung bodies were perfectly adapted for tackling the tough, fibrous ferns, cycads, and shrubs that carpeted the forest floor. One group harvested the canopy, the other tended the undergrowth. This elegant separation of feeding strategies allowed the Cretaceous Commons to support a density and diversity of megafauna that remains unparalleled in Earth's history. A carefully balanced ecosystem built on a shared but partitioned menu. The success of these herbivorous dynasties was built not just on individual adaptations, but on the power of the collective. Fossil evidence, from vast bone beds containing thousands of individuals to extensive trackways crisscrossing ancient floodplains, paints a vivid picture of complex social lives. These were not solitary creatures. They lived in structured herds that could number in the thousands. Such large groups offered significant advantages, most notably protection through shared vigilance. With hundreds of pairs of eyes and ears on the lookout, the approach of a predator was less likely to go unnoticed. Furthermore, discoveries of nesting grounds, like those of Maiasaura, the good mother lizard, reveal a high degree of parental care. These sites show organized colonies with nests built in close proximity, suggesting communal nesting and protection of the young. The sounds of this world must have been extraordinary. A cacophony of the deep, resonant calls of hadrosaurs echoing through the forests, mixed with the grunts, bellows, and rustling of the great ceratopsian herds. It was a world bound together by intricate social fabrics. Life in the Cretaceous Commons, for all its abundance, was lived under a constant, looming shadow: the presence of apex predators. The sheer biomass of herbivores provided a staggering food resource for carnivores, culminating in the evolution of one of the largest and most powerful terrestrial predators of all time, Tyrannosaurus rex. Survival for the great herbivore herds depended on constant awareness and effective defense strategies. For a herd of hadrosaurs, the primary defense was detection and flight. Their keen senses and the safety of the crowd meant an alarm call could trigger a stampede, a thundering wave of flesh that would be difficult for any predator to target effectively. Ceratopsians, however, were built to stand their ground. An adult triceratops was not easy prey. When threatened, a family group could form a defensive circle, presenting a wall of bone, horn, and muscle to any would-be attacker. These confrontations were likely dramatic, high-stakes contests of nerve and strength, with the predator weighing the risk of severe injury against the potential reward of a meal. This predator-prey dynamic was the engine of evolution, shaping the very anatomy and behavior of these magnificent creatures. For over 15 million years, the hadrosaurs and ceratopsians were the heart of the late Cretaceous ecosystems in North America and Asia. Their evolutionary innovations, the dental batteries of one, the horns and shields of the other, allowed them to unlock the full potential of the Cretaceous floral boom. Through sophisticated niche partitioning, they created a stable and resilient commons, a shared planetary pasture that supported an entire food web, from the smallest scavengers to the mightiest predators. Their story is a powerful illustration of coevolution, where plants and the animals that eat them shape each other's destinies on a geological timescale. The herds that thundered across these ancient plains represent one of the great pinnacles of vertebrate life on Earth. Though their world came to an abrupt and catastrophic end, the ecological blueprint they established endures. The dynamics of large herbivores shaping their environment, dividing resources, and living in complex social groups is a pattern that nature has repeated, a timeless theme played out on the savannas and prairies of our own time, a distant echo of the great dinosaur domains. In the fading light of the late Cretaceous, the world was a mosaic of sensory information. For Tyrannosaurus rex, this landscape was not just a hunting ground. It was a domain, a territory etched into its very being. 66 million years ago, the air itself carried messages. The scent of pine and damp earth, the distant smell of a carcass, the subtle musk of other giants moving through the trees. T-Rex processed this world through senses honed to an extraordinary degree. Its eyes, positioned for superb binocular vision, perceived depth with an accuracy few creatures could match, turning the dense foliage from a wall of green into a three-dimensional map of opportunity and threat. Its hearing could detect the low-frequency sounds of heavy footfalls miles away. But this was more than just a passive sensory experience. It was an act of constant surveillance. Every sound, every scent was a data point in the complex calculus of survival and dominance. To rule this territory required not just overwhelming power, but an intimate, moment-by-moment understanding of its rhythms, its inhabitants, and its ever-present. This was the tyrant's kingdom, and vigilance was the price of the crown. But this kingdom was far from empty. It was shared with contemporaries who were anything but helpless. These were the armored titans, herbivores built not for flight, but for confrontation. Chief among them was Triceratops horridus. Weighing as much as a bull elephant, it was a walking fortress of muscle and bone. Its iconic three horns were not merely for display. Pathology on fossil skulls suggests they were used in combat, both against rivals and predators. Behind this formidable weaponry was a massive shield of solid bone, the frill, protecting its neck from attack. It moved with the assurance of a creature that had little to fear. Equally challenging was the low-slung Ankylosaurus. This animal represented a different evolutionary solution to the same problem. It was covered from its eyelids to its tail in a pavement of osteoderms, bony plates embedded in the skin, creating a nearly impenetrable shell. And at the end of its powerful, rigid tail was a club of solid bone, capable of swinging with enough force to shatter the leg of an adult T-Rex. These were not simply prey. They were co-inhabitants, powerful forces of nature who contested every riverbank and clearing. Our understanding of these ancient conflicts is not born from imagination, but is etched in stone. The fossil record serves as a silent witness, providing definitive evidence of violent encounters. Paleontologists have unearthed Triceratops skulls bearing the unmistakable signature of a Tyrannosaurus attack, deep puncture wounds and long scrapes across their bony frills. Crucially, many of these wounds show signs of healing. This tells a remarkable story. The Triceratops was attacked, it fought back, and it survived to carry the scars of its battle for weeks, months, or even years. These healed injuries are forensic proof of non-lethal confrontations, likely territorial disputes or failed predation attempts where the herbivore's defenses proved superior. The story is not one-sided. Tyrannosaurs themselves bear similar scars. Healed bite marks on their own skulls, matching the teeth of other tyrannosaurs, suggest that brutal, face-biting combat was a common feature of their lives, likely over territory, mates, or resources. The bones do not lie. They speak of a world where conflict was a constant and survival was never guaranteed, even for the apex predator. Let us reconstruct a scene guided by this fossil evidence. A large adult Tyrannosaurus, driven by thirst, approaches a familiar bend in a wide, slow-moving river. But the path is blocked. A massive bull Triceratops stands knee-deep in the cool water, its bulk displacing the current. There is no immediate charge, no explosion of violence. Instead, a tense and calculated negotiation begins. The Tyrannosaurus lowers its massive head, perhaps emitting a low-frequency rumble too deep for human ears to perceive. It's a display of size and potential force. The Triceratops responds in kind, not by retreating, but by turning to face the predator, presenting its 3-foot-long brow horns as a clear statement of its capabilities. It scrapes a powerful forelimb on the riverbed, stirring up mud. This is not a prelude to a hunt, but a complex behavioral interaction, a contest of nerves. Each animal assesses the other, weighing the potential cost of escalating the conflict. In this moment, they are not predator and prey, but two monarchs of the same domain, grudgingly acknowledging each other's power. After a long, tense standoff, the Tyrannosaurus, judging the risk too great for the reward, turns and moves downstream. The territory has been successfully defended. The challenge posed by an Ankylosaurus was of an entirely different nature. It was a living citadel. Confronting this animal was less a physical battle and more a strategic problem. Its low center of gravity made it almost impossible to tip over, and its broad, heavily armored back offered no purchase for a Tyrannosaurus's jaws. A direct assault from above was futile. The tyrant's legendary bite force, capable of crushing bone, would be wasted against this shield of interlocking osteoderms. The only potential vulnerability was its unarmored underbelly. But to get there, a predator would have to navigate the lethal arc of its tail. This appendage was no simple club. It was a complex and powerful weapon. The final vertebrae were fused together into a heavy knob of bone, powered by enormous muscles. A well-aimed swing could connect with devastating impact, shattering bone and crippling an attacker. A Tyrannosaurus would have to be patient, intelligent, perhaps even lucky to find a way past this active defense system. The Ankylosaurus forced a change in tactics, demanding strategy and precision over sheer power. While healed scars tell stories of survival, other fossils chronicle final moments. Unhealed bite marks are the paleontological equivalent of a smoking gun, capturing the destructive power of a successful attack. In the collections of museums around the world lie the bones of herbivores like Edmontosaurus and Triceratops that bear these fatal signatures. One remarkable specimen, a vertebra from a hadrosaur's tail, contains the broken-off tip of a T-Rex tooth still embedded within it, surrounded by bone that shows no sign of healing. This animal did not walk away. These discoveries allow scientists to do more than just confirm the predator-prey relationship. They allow us to quantify it. By analyzing the depth and shape of these gouges and using biomechanical models, we can calculate the tremendous force of the T-Rex's bite, an estimated 6 tons of pressure per square inch. This was a bite capable not just of shearing flesh, but of explosively shattering the very bones of its target. Each unhealed wound is a stark reminder that while standoffs and strategic retreats were common, the tyrant's territory was ultimately a place where life and death struggles unfolded with brutal finality. The relationship between Tyrannosaurus and its heavily armed neighbors was far more intricate than a simple tale of hunter and hunted. It was a multi-generational arms race, a powerful engine of co-evolution played out over millions of years on the floodplains of ancient North America. The immense predatory pressure exerted by T-Rex likely drove the evolution of even more elaborate defenses in its prey. The horns of Triceratops grew larger, its frill more robust. The armor of Ankylosaurus became thicker, its tail club more massive. These were evolutionary responses to a persistent and intelligent threat. In turn, Tyrannosaurus itself was shaped by these challenges. A predator that could successfully tackle a living fortress had to be more than just powerful. It had to be adaptable, cunning, and resilient. The result was not a world of constant mindless violence, but a complex, dynamic, and surprisingly stable ecosystem. It was a shared planet where the tyrant's reign was held in check by the formidable defenses of its subjects, creating a precarious and magnificent balance of power, right up to the very end of the age of dinosaurs. The Mesozoic era is often envisioned as a static, tropical paradise, a perpetual summer stretching for millions of years. But the reality, preserved in the subtle language of rock and fossil chemistry, was far more dynamic and demanding. This was a world of profound seasonal change. Great monsoonal rains would inundate entire continents, transforming dry plains into vast wetlands, only to give way to punishing dry seasons that baked the earth and withered vegetation. And nowhere were these shifts more extreme than near the poles. During the late Cretaceous, high-latitude ecosystems in what is now Alaska and Siberia experienced months of continuous winter darkness. Though global temperatures were milder than today, the extended lack of sunlight halted photosynthesis, turning a vibrant green world into a realm of frozen scarcity. For the dinosaurs that called these regions home, this was not a challenge to be endured in place. It was an undeniable signal, a primordial command, written in the angle of the sun and the whisper of the first cold wind. The command to move. This was the powerful engine that drove the greatest journeys the world has ever known. The response to this celestial command was a thundering river of life. For creatures like the horned Centrosaurus, survival was a collective endeavor, their social bonds forged on the anvil of necessity. Tens of thousands, perhaps hundreds of thousands, would gather, their low calls a constant, resonant rumble across the plains. This was not a chaotic stampede, but an organized, instinct-driven procession, with its own internal logic. The herds followed ancient paths, corridors of favorable terrain etched into the landscape over generations of use. They moved with the shifting patterns of vegetation, pursuing the green wave of new growth that followed the rains or the spring thaw with unerring precision. The journey was a living chronicle of their existence, a testament to their social complexity. The strong protected the weak, forming defensive circles around the young, while the experienced guided the massive column. They crossed vast floodplains that would soon become parched mud, and forded braided rivers whose currents were a constant test of strength and endurance. Each step was a gamble, a colossal investment of energy for the ultimate prize, a land of temporary plenty. This immense, moving banquet of herbivores did not travel alone. The great migrations created their own mobile ecosystems, and trailing in their wake like patient shadows were the apex predators. For a tyrannosaurid like Albertosaurus, the herds were a predictable, seasonal resource, a larder on the move. But this was not a relentless, high-speed chase. Such pursuits were energetically unsustainable. Energy was a currency no predator could afford to waste. Instead, they shadowed the herds from a distance, using ridges, forests, and ravines for cover. They were strategists, keen observers of animal behavior. They watched for the subtle signs of weakness. An individual lagging behind with an old injury, a juvenile separated from its mother in the confusion of a river crossing, an older animal faltering from the strain of the relentless journey. Their pursuit was a war of attrition, a patient game of capitalizing on opportunity. The presence of these great carnivores added a palpable tension to the migration, a constant pressure that culled the herd, ensuring that only the most resilient would reach their destination and pass on their genes to the next generation. The arteries of this prehistoric world were its great river systems. These waterways were both highways and hazards, defining the routes of migration with absolute authority. They offered vital water and lush gallery forests along their banks, concentrating life in vibrant linear oases that snaked across the landscape. Many herds would follow the course of a single river for hundreds of kilometers, their journey guided by its life-giving flow. But these corridors held their own ancient dangers. Crossing them was a moment of supreme vulnerability, a necessary risk where the entire herd was exposed. And lurking beneath the placid, murky surface was an older, more patient form of predator. The colossal crocodilian Deinosuchus, an ambush hunter of terrifying efficiency, ruled these waters with absolute power. Growing to the length of a bus, it could remain perfectly still, a submerged log of immense potential energy, waiting for the herd to approach the water's edge. A single moment of incaution was all it required to unleash its explosive power. These aquatic sentinels were a formidable filter, another of nature's harsh tests that migrating dinosaurs had to pass to complete their epic cycle of movement. Not all migrations were a hurried exodus against a ticking seasonal clock. For the largest animals to ever walk the earth, the sauropods, the journey was a slower, more profound affair. A creature like the colossal Alamosaurus did not rush. Its physiology and immense energy requirements dictated a different rhythm. Theirs was a gradual, continental drift, a slow-motion pursuit of browse that spanned vast territories from uplands to coastal plains. A single herd could influence the ecology of an entire region, their presence altering the very structure of the environment. As they moved, they were ecosystem engineers on a planetary scale. Their immense weight compacted soil. Their passage carved new paths through dense forests that smaller animals would later use. And their high-browsing feeding habits pruned vegetation, opening up the canopy and allowing sunlight to reach the forest floor. This, in turn, created opportunities for different plant species and the smaller herbivores that followed in their literal footsteps. They were living, breathing forces of nature, whose seasonal wanderings were less a migration and more a slow, deliberate reshaping of the world around them, their progress measured not in days, but in the turning of the seasons themselves. While the earth-shaking tread of the giant herds dominated the terrestrial landscape, the skies and the undergrowth were alive with their own myriad travelers. Migration was a universal principle, a fundamental solution to the problem of shifting resources, scaled to the size and needs of every creature. Great flocks of pterosaurs, like the gigantic Quetzalcoatlus with its aircraft-like wingspan, rode the thermal updrafts, soaring across continents with breathtaking efficiency and minimal effort. Their journeys may have been tied to coastal nesting sites or the seasonal abundance of fish in great inland seas. On the ground, smaller dinosaurs, early mammals, and reptiles undertook their own localized migrations, moving from drying floodplains to the cooler, more humid refuge of upland forests. Even life that couldn't walk or fly was part of this grand circulation. Plant seeds and spores traveled on the wind, or, more effectively, in the digestive tracts of dinosaurs, colonizing new lands hundreds of kilometers away. The entire planet was a dynamic web of movement, a complex choreography where every living thing was bound by the same fundamental need to follow the resources. This was the very pulse of the Mesozoic world, a planet breathing in a rhythm of seasons, its lifeblood the ceaseless, patterned movement of its inhabitants. These migrations were the intricate rules that governed a shared world, a complex dance of interdependence where the path of the hunter was dictated by the hunted, and the growth of the forest was shaped by the giants passing through it. This was no lost Eden of tranquil stasis. It was a dynamic, challenging, and deeply interconnected globe, where survival depended on mobility, instinct, and adaptation on an epic scale. The evidence for these epic journeys remains today, etched into the very bones of the earth. Vast bone beds speak of herds that perished together in a flash flood or volcanic event, and fossilized trackways, frozen in ancient mud, mark their ancient highways. They are the silent, powerful testimony to a river of life that once flowed across continents. These are the echoes of their world, a profound reminder of the timeless, fundamental laws of nature that connect all life, past and present, on a planet defined by change.